Well, welcome back. We have a new idea.
Yes.
I love new ideas. We have mastered basically one concept in section 13.3 called the partial derivative. The partial derivative, it is a derivative in a direction, but only very specific directions. What two directions do we typically think of a partial derivative in?
X, Y.
Yeah, we hold the x constant or we hold the y constant, and we get, I did that backwards, but we hold the y constant or the x constant, we get the derivative along the surface, but restricted to a curve created by a plane that is parallel to the xz plane. Or we get the derivative, the slope of the tangent line, to a curve along the surface that's held constant by a plane that's parallel to the yz plane. That's the two things we got. So we've talked about directional derivatives, but only in two directions. Now we extend the concept. How do we go about finding directional derivatives or derivatives in any direction? That's what we discussed today. We're going to talk a lot about the why, a lot about the where it comes from, a lot about the how, and not a whole lot about the practice of it yet. That's next time. So right now I want to derive it. I'll derive the directional derivative. So, hey, in order to take and get a directional derivative, we've got to give it a direction. What in calculus gives us a direction? Just leave it right there. What in calculus gives us a direction? Vectors. Let's give this thing a vector. Let's make it this way. To give a directional derivative a direction, we need a vector. Bless you. Thank you. Let's have a vector. Now, let's be more specific. Let's call it a unit vector, because I don't want the length of the vector to affect my slope in any way. I don't want that to happen. So I want the length to be 1 so that we don't magnify the slope accidentally. So let's take a vector, but more specifically, let's take a unit vector. On the plane of the independent variables. So in other words, we go, okay, well, what direction do you want? Find me a vector. Where's the vector going? Only on the xy plane. That's all we need. We just need the vector to go somewhere on the xy plane. The dependent variable is going to be affected by all the xy stuff anyway, and that vector is built into that. So we don't need a vector going through space. That's not the idea. The idea is, give me a direction somewhere on this xy plane, and then we can build a directional derivative from that. Idea, head nod if you get that idea. Just a little side note, just to prove my point. If this is a unit vector like that, just a side note, please note, D, let's call it F, with respect to X, or this is not notation, just either or, with respect to X or with respect to Y, these were directional derivatives. Well, wait a second, Leonard. That's Professor Leonard to you, all right? So wait a second, Leonard. If they're directional derivatives, you have to have a unit vector for the direction. Everyone in class right now, what's a partial derivative with respect to x? What direction is it in? X direction. What's the unit vector in the x direction? I. It was a directional derivative. It was a vector in the x direction. It would just be I. So these are directional derivatives where u was just equal to I or j, respectively. That's the same thing. So that was that was just very specific. That was. Do you guys get the point of what I'm talking about here? They said, yeah, you know what? You restricted along x or y. That's a vector this way or that way. Those were just our partial derivatives with respect to x and y. They were directional. It was just very, man, almost like two-dimensional, if you will. It wasn't universal. Now we're speaking more general. Now we're saying, okay, if I want a directional derivative, to give a direction, we got to have a vector. We got to call it a unit vector, just like this and this were unit vectors. Otherwise, we affect the size of our slope, and we don't want to do that. So let's start with just some random unit vector. So there's our direction, right there. So what we're going to try to do is we're going to try to build a tangent line through a point going in this direction, or having this direction. You guys understand the idea? So we've given the slope, if you will, the slope of the tangent line to the surface of the point, a direction. It's called u, just a unit vector. Now, here's what we need to find all this stuff. Man, you know this, right? To find a point, you need a direction and you need a point. So we're going to give this thing we're going to give it two things. So here's our idea. Things we need. Number one, we need a unit vector. Number two, we need a point for a specific rate of change. Let's do it. Let's give it a point. By the way, I want to talk to you about this one. That point P is going to be on the xy plane. It's going to be on the plane of your independent variables. So this is on xy. And now if you're okay with that so far. So we're starting out, we're saying, hey, you know what? I want to find the slope of a surface, but only in a certain direction. I'm going to give it a direction. It's called u. This is a unit vector. It's on the xy plane of independent variables. I got a point P. It's on the xy plane, the plane of your independent variables. And we go, how about this idea? Let's take a line through the point P parallel to u in the same direction. Can we do that mathematically? Of course we can. That's exactly how lines are defined. It says I'm giving you a point and a vector. You can define me a line that goes through that point in the direction of that vector. And now if you're okay with that one. This vector will not have a z component. So it's even easier. It's just a parametric line. That's all we're talking about. So let's take that. So let's take a line. Through P parallel to u. There's my line through P parallel to u. And now if you're okay with that so far. What this is going to do, man, just imagine this for a second. Imagine this line that I just made. Notice how it's going through point P. Imagine this creating a plane, vertical plane in the z direction. Can you imagine that here real quick? That plane is going to intersect this surface. Do you see it? It's going to do it. It's going to look something like this. So if I take this, so make a line through P parallel to the unit vector u, what this is going to do is create a plane parallel to the UZ plane and we're going to figure this out in a second. That's pretty good to me. Bless you.
Thank you.
That does something. Bless you again. That's enough out of you. You've reached your quota of sneezes. Was it the same person though? Oh dang! Is it allergic? Is it catching? I'm out of here. We want a direction other than I or J. Okay. Give it a different unit vector. Those were unit vectors. Just give it a different one. Like, okay, I still want a point. I know it's on the plane. That's a little confusing for you right now, but trust me, it'll make sense in just a minute, okay? Put another point somewhere on there. You have to have a specific point to find a specific rate of change. Does that make sense? So we're giving it a point. Make a line through that point parallel to the unit vector that you want. No problem. We literally did that with partial derivatives. We literally said, hey, parallel to x or y. We've already done it. Now it's just parallel to u. It's going through the point. Head nod if you're with me on that one. Now, what that creates, if I let that thing float up and slice the surface, it's going to create a plane parallel to the UZ plane. Can you picture the UZ plane up here somewhere? This is parallel to it, just set back. What that's going to do is intersect my surface, and what happens when you let a plane intersect a surface? What do you get? Do you get another plane? Do you get another surface? What do you get?
Curve.
Can you see the plane cutting the surface? What's this outline of the plane on the surface?
Curve.
It's a curve. That sounded way too. It's a curve. It's a curve. But how about this? Can you find derivatives of curves? Can you find derivatives of curves that are on freaking planes? Boom, we have the idea. So what this does, it creates a plane parallel to the UZ plane. Yeah, it's parallel, just set back a little bit. It's going through the point. It's going to cut our surface right here. Parallel to the UZ plane that makes a curve on the surface contained by a plane. Makes a curve on the surface in the plane. Let's continue. Here's what I want to do now. Now, I'm going to tell you something in just a second, but here's what I want to do now. I want to do like this sort of reverse projection. I want to take the point P, I'm going to look from underneath, I'm going to shoot it right through the surface. What's going to happen so if this is the point P down here, I'm going to get this projection, let's call it P prime. Can you see that P prime is directly above the point P? Head nod, yes, no. To be honest with you, we kind of worked backwards here. Well, how I want you to really think about it now is that P is the projection of P prime onto the plane. We just worked backwards. We said, yeah, give it a point. Can you do it? Yeah, I can. It's just the projection of some point on the surface. Does that make sense? That's what we're doing. That's it. So P prime will be mapped to, P will be mapped to the surface, P prime. I'm not going to write anything out for it. That's all we're doing. We're just mapping this to here, and the P is the projection of P prime. It's possible we just did it. Let's also do one more thing. Let's let Q be on this line right here. This is going to start coming to a head here real fast. Let's let Q furthermore be mapped also to the surface. Q prime. Let's call it Q prime. I have some important questions. I'm going to write some stuff out, and then we're almost done with our proof. All right. So here's important questions. Are P prime and Q prime both on the surface? Are P prime and Q prime both on the same curve?
Yes.
Is that curve contained in one plane?
Yes.
What plane? UZ plane? Parallel to the UZ plane. Well, maybe the PQ plane, I don't know, PQZ plane, whatever that is. The vector here with the Z vector. It's slicing the surface. We got a curve on the surface. Those 2 points are on the surface, on the curve, in the plane. Show of hands if you're okay with that one. Let's write one thing out about that, and then we're going to move. So here's what I want to know. If I were to create a line, gentlemen, if I were to create a line between these 2 points, is that a tangent line? Here's my goal. My goal is to find the tangent line at P. If I make a line like this, I don't want to mess up my picture, but if I make a line straight down here like this, connecting P and Q, is that a tangent line? What do we call that in calculus? Okay, so P prime, Q prime, that's a secant line. But it's in the plane. It's a secant line, but it's in the plane. Now, what has to happen? What has to happen in order for this secant line to be a tangent line at P prime? What's got to happen? What's got to happen? What has to happen to those 2 points? They have to get closer. How do I make, watch carefully, I don't like, there's some people who are going to misunderstand this, okay? Because I'm going to point to 2 different points, and you need to understand what's going on. What I want to happen, I want this to be there. I want this point to get really, really, really close to that point. Are you with me? How do I make that happen? I don't make this move, I make this move. If I make Q get really close to P, can you see that since these are on the same curve, they're projected upwards, that Q prime is going to get really close to P prime? Can you see that? So if I let Q go to P, the secant approaches the tangent at P prime. Get that sorry, get that right in your head. I'll say it one more time. I want the tangent here. This point needs to get really close. How close? Really, really close. How do I move it? Well, I've got to move it based on my independent variables. These are based on dependent variables. I got to move it here. If I move Q close to P, Q prime gets really close to P prime, and the secant approaches the tangent at P prime. Yes?
Can we only move Q? Can we not move Q prime to move Q?
We are moving Q prime, but it has to, let me ask you something. When you move something in a function, do you move the dependent variable or the independent variable? Independent. Right now, we have to move the independent variable to move the dependent values. Make sense? That's why we project upwards and work backwards. That's why we have our primes here and our actual points there. So I can move these ones. Let me write this out, and then we're going to get back to it. So yeah, P prime, Q prime, that's secant. If I let Q approach P. So let's do this one. There's only a couple more things. We got to talk about 2 more concepts, and then we do a little bit of math. I prove the idea of the derivative, and then I show you a nice way to do it that relates back to differentials, and we're done for the day. We're not going to have a time for an example today, but it's going to be really easy to come back to this thing if I finish this little part, okay? So stick with me here. You guys okay on the idea up to here? I don't really want to repeat it, but The idea now is we got to get this point here. We're moving these things. However, watch what's happening here. Watch what's happening. From P to Q, we also have two changes. You see, we don't just have a change along the X and a change along the Y anymore. We got a change along both of them. Here, it was just X. Here, it was just Y. Here, it's crap. It's delta X and delta Y. There's a change there. So what's it going to take to move Q close to P? What do both of those delta X's and delta Y's have to go to? Come on, quickly. What do they have to go to? They have to go to 0. I can't just move delta Y to 0. The point's going to be over here. I can't just move delta X to 0. The point's going to be over there. I need to move both of them to 0 to get this to go to there. Are you with me? So again, the idea is weird, all right? But the practical idea is not weird. The practical idea is take a vector, give me a line, project it upwards. It's creating a curve. We can find derivatives of curves on planes. That's exactly what it is. How do you do it? You make one point get really close to another. So if we're going to find the tangent of P prime, we want this point to get really close to that. How close? Really freaking close. How are we going to move it? Well, you can only move points, values like this, based on their independent variables. Down here. So I'm moving Q to P, and these respond by moving Q prime to P prime. This gets close to here. This gets close to there. It responds by moving. That's how dependent variables work. They respond by changes in your independent variables. Are you with me? How do I do it? How do I make this go to... Well, there's two changes. X has to change, and Y has to change. And they've got to both become 0. Does that make sense? So, to move this, to do this, since there's multiple changes here, to move Q to P, I've got to let both delta X and delta Y go to 0. Please keep in mind, please make a note, if you didn't catch it the first 7 times I said it, this is not Q prime and P prime. Q prime responds by moving Q to P. Does that make sense? I'm talking about these values. The only way I can move these values is by letting delta X and delta Y go to 0. That's what I'm doing here. Now the last thing. The vector PQ, true or false, the vector PQ that creates a line is parallel to the unit vector. Dead true. That's how we made the line in the first place. Same direction. Tell me something you know about vectors that are parallel. They're scalar multiples. Absolutely, they're scalar multiples. So, if PQ equals, well, let's look at it. Oh my gosh, all of our vector junk is coming back to bite us and, help us a lot. A vector from here to here can be separated by a sum of vectors here and here. Do you see it? Delta x along the I direction, delta y along the j direction. So PQ can be redefined as delta xi plus delta yj. That's how vector addition works. However, if this is true, if they're parallel, then this vector has to be a scalar multiple. It's called h. Scalar multiple times u. That's what parallel means. You just said it. You just said parallel vectors have to be scalar multiples of one another, correct? Well, let's work down this side here for a second. U could also be thought about as being along the x and the y. That's how vector addition works. So this could be thought of as h times u1i plus u2j. The x component along the I, the y component along the j. Same stuff. But that means this. If these two things are equal, and I distribute my scalar, it's possible we can do that. I hope that you follow this. It's kind of a little bit disjointed, but it flows this way. These are parallel, they're scalar multiples. Scalar multiple of u means this. If PQ is this, and PQ also equals a scalar multiple of u, then these two pieces are equal. Did you catch that? But then one more thing about vectors. If vectors are equal, their component pieces must be equal. Now, why in the world are we doing that? Here's the whole shebang. Because a lot of people miss it and they go, what is this stuff coming from? Where did you get the H? H's are scalar. How did I get this similarity? How did I get this equality? Parallel vectors. Components equal scalar multiples of each other in parallel vectors. They have to. Why are we doing it? Here's the why. Here's the why. Here's what people lose. People just kind of skip the section of the book and they get to the how you actually do it. Here's the why. I don't want to have to base my derivative, the doing it, I don't want to have to base it on this line. Because finding the vector of this line, I don't even have another point. Do you have 2 points? No. You just have 1 point to find the rate of change at that 1 point. And then you'll be given this other vector. I don't want to have to do this. Make a line through P, find the vector, find another point, and then do all this crap with it. I don't want to do that. So what we're trying to do is say, let's base this derivative through this point, but based on this vector only, and this is the map that lets me do it. Instead of talking about delta x, forget that. Let's talk about a number, h, times the first component, the x component of u. That lets me base my derivative on the u and not on this random vector through the point. Do you guys see the point? Sorry. But that's the idea. So let's go with it. We're going to write the derivative one time of how slope works, and then we'll change it to be based off of this, and then you'll see how everything is magically glorious, and I'll give you the definition of the derivative. Yay, fantastic. So, definition. Here's how derivative looks normally. We take a derivative, can't even really write it that way. How would we write it? Times, no, plus, and kind of. Well, I'm kind of making stuff up. Some expression, and I'm just making up my own math. That's never a good sign. I'm going to use this to represent some expression of delta x, delta y. Why? Because, well, I'm kind of thinking out loud here that it's Pythagorean theorem. You take that distance and you shorten it. We can do it that way, call it 0. But it's really hard, and you see why it's really hard to define this derivative based on two things changing. Because in limits, you have to change to a point. We don't have an actual point. We have just change in x and change in y. We want them both to go to 0 at the same time. We go, how do I represent the denominator? Well, that change, what's changing? Both of them. It's hard to define that. You can use Pythagorean theorem to define this change and let that go to 0, that's fine. But here's the whole point. Here's the whole point. Some of you guys are losing focus. Don't lose focus here. This is the big deal, okay? You could have ignored all of this crap, and then right here, focus in now. Now, this is the if you are ever doing anything involving derivatives, you're taking the height. Let's verify this is the height based on the plane. Here's the height at this point, delta x plus delta y. Here's the height at this point, minus the height at this point. Yeah, it's a little bit off, but here's the change in height, that's this, divided by the change in run. That's this distance, that's this. That's that Pythagorean theorem I was just talking about. We're letting that go to 0. Your denominator has to be 0. So if you want to look at this is slope. That's what it is. It's change in height divided by change in rise divided by change in run. Well, we always let the run go to 0 for derivatives. What happens when it gets really, really small? But that's awkward to work with. I don't want to do that. Especially since that's probably Pythagorean theorem, delta x squared plus delta y squared inside of the square root. It sucks. But what can we do? Use this. Every place we now see delta x, replace it with this. Every place we now see delta y, replace it with this. And let's see what happens. I want to see if this works. Hang on, let's see. Oh man, that's beautiful. You know what? I'm going to do it. I've never seen this before, but we're going to do it. So I'm going to make it up. It's going to be freaking awesome. Oops, no. Bad letter. Because I really want you to see the slope at work. Do you guys see the slope? Change in height along this plane, change in run along this plane. That's just a distance formula. This squared plus this squared square root, that's Pythagorean theorem, just for whatever you want to do. And then we go, hey, let's make it go to 0. That's what's happening here. You follow? If x and y, delta x, delta y both approach 0, this thing approaches 0, we get the idea of the derivative. That's the idea. This is the definition for the derivative of any curve, like freaking ever. And this is a curve on a plane. You follow? Here's the magic. Watch this. We're going to do some math magic right now. That's pretty cool. Because how do I get from here to here? How does it happen? Watch. If delta x is this, and delta y is this, and I have them in the square root, can I factor?
Yes.
Yes.
I'm getting excited. Can I simplify? Tell me right now, what is the vector u? Tell me right now what it is. What type of a vector is it? What's the magnitude of a unit vector?
1.
What? Boom! You don't see it. Oh crap! I kind of went too fast on that one. If this is a unit vector, then the component. Do you remember how to find magnitude of vector? Square them, add them, square root them. If it's a unit vector, this magnitude has to be 1. So this whole piece changes to h. How does it work? Let's let the h go to 0. Notice if the h, the scalar that I put in my problem, if h goes to 0, delta x goes to 0. Delta y also goes to 0. Our derivative works. Now, if you're like, why in the world are we doing this? This is stupid. Why do we waste all the time when we already have that? This right here is based on this vector, which is impossible for us to find because we do not have 2 points. Or, not impossible, but you have to create it by making it a parallel line through that point. That sucks. This derivative is based on that vector, and that's what we wanted. So all we need to find derivatives, look at what we need. We need a function, and we need a vector. That's it. Just a unit vector. We need a function for this, a unit vector for that, and h goes to 0. That's the idea of a directional derivative. Now, I'm not going to derive the rest of this, but I want to show you how we do it. The question was asked, do we have to do derivatives based on limits again? Please say no. Please say no. Yeah, no. No, we don't. Okay. Just like all calculus ever, there's easier ways to do it. I wanted you to walk through this so you understand the idea, where it actually comes from. Do you understand the idea where it actually comes from?
Wait.
this is what we call a directional derivative of a function of two variables along a unit vector u. That's how we write it. How we actually do it. It was kind of cool of us to do it this way. Because we defined that vector as being delta x, delta y, because we did that, we get to think of these as partial derivatives kind of added together. If you think about that, that's what p and q were. They were, vectors were separated, right? Along the x and along the y, and then we added them. That's what we do here. We take a partial derivative along the x. We take a partial derivative along the y. Does that look familiar to you? Does it? It should, because if I do this, don't write this down, but just watch. If I do this, what's that? Sorry. What's that?
Different function.
Okay. Now this was exactly the same as that, correct? However, we used two things over here to substitute these guys for. We based them on those, the components of u. That's why we wanted to change down to the u's, so that all I have to do to find a directional derivative is take a partial derivative. Do you know how to do that? Take a partial derivative. Do you know how to do that? You know how to find the component of a vector? Multiply. Component of a vector, multiply, done. That's how we actually find directional derivatives. It's not hard. It's really easy. I know I could have given that to you. If you wanted to just go to here, that's fine. But you're not in this class to just go to here. You're in this class to actually understand what the heck is going on behind it. That's what the heck is going on behind it. Did it make sense talking about this stuff? There's a big note, and then we're going to be done, I promise. The big note is this. What type of a vector is u? U's got to be a unit vector. Otherwise, this does not work. And that's a problem. So we're continuing. We're on this new stretch. We're saying let's find derivatives, but not just along the x and the y, along a different two-dimensional vector. X and y are two-dimensional. I and j are two-dimensional. U is also two-dimensional on the plane of your independent variables, your x-y plane. So basically, what we said the whole last part of last class, getting to this point, was suppose that you have this function. This function creates a surface. Do you see it? Two independent variables, you are creating a surface. Take a vector, a unit vector. It has to be a unit vector. It matters. It really matters. Take a unit vector, look at the two components. They are 2D. Take a unit vector on your xy plane. Take a derivative, basically, that creates this tangent line right over that vector. I spent a lot of time last class going between delta x and delta y and getting to u1 and u2, the change on that exact unit vector. So that's what we spent our time doing. We're creating this unit vector on 2D, taking our surface, and then creating this plane that's right over that unit vector and finding the tangent line in the direction basically of that unit vector projected onto the surface in this case. And now if you're okay with what I'm talking about. If you do it right, the derivative, so the slope of the tangent line that you would get through a point, if you project it downward, would lay right on top of that unit vector. That's what we're talking about. Or parallel to it, if you will. That's what we're trying to do. So we made it that far last time. Now, I'm going to change it a little bit, because this is not actually what we do. I'll make it even easier. It's pretty easy. That's literally just an x component. That's literally just a y component. That's a partial derivative with respect to x, partial derivative with respect to y. You jump them together, and you're done. That's how a derivative works here. That's a directional derivative for us. Not that bad. I'll make it even easier. And the reason why I'm going to do that is because we have a part that we're going to create that's really, really useful for a lot of stuff that you're going to be doing in your engineering, physics-y type, calculus-based classes. We're going to get to that in just a second, okay? So let's start with just one example. Let's start with this one. Find a derivative of that thing at that point in the direction of the vector that makes an angle of that with the x-axis. Now, we haven't talked about this very much, but if you remember, there was a way to find a unit vector when I gave you an angle. Do you remember how to do that? It was a long time ago, like chapter 11 stuff, way back. Well, let's go through it, but let's start with what we need. In order to figure out an actual slope of a tangent line to a surface at a point, you need two things for this case. You need a point. Do we have a point?
Yes.
What's the point?
2.
Yeah, notice that point is on the xy plane. You could figure out the point on the surface by plugging in 1, 2 and getting 1, 2, whatever that is. You can plug it in and figure it out. So we need a point to at least figure out a point on the surface, and we need a vector to get a unit vector to give us the direction that we want to climb that surface. Does that make sense? We want to climb the surface at this direction or this direction based on the unit vector. So number one, we got a point, no problem. So our point is 1, 2. That's an x value, y value we'll be able to plug in. That's what we want first. Next, we got to find u. So the two things we need, a point, got it, and a unit vector. If you don't remember how to find a unit vector, I'm going to give you the formula. It's seriously not hard. We'll write it over here for a second. A unit vector, when we have an angle, positive angle from the x-axis, can be written as cosine theta I plus sine theta j. That was earlier in our work from chapter 11, but that's where we get that from. Here's what I want you to do right now. Can you take the angle, put it in here, and give me a unit vector? Can you guys do that?
Yes.
Let's do it real quick. I'll give you about 30 seconds. Plug it in, get me the unit vector. Did you do it? Right-siders, what's cosine of pi over 6 real quick? Left-siders, what's sine of pi over 6? What do you got out of that one? Head nod if you're okay on finding root 3 over 2i plus 1/2 j. Hey, is that a vector? Yeah. Is it a two-dimensional vector? Yeah. So what we're doing is we're saying, hey, here's your surface. Let's find this unit vector, create a tangent line right over that, or at least parallel to that. That's what we're doing here, climbing the surface. So if we have a point and we have a unit vector now, what we're going to do is we're going to try to figure out what our directional derivative is by doing that. So I want to start building this out right now. I'd like you to find the derivative of f with respect to x and the derivative of f with respect to y. Just write it right below that. Middle people, can you guys help me out here? What's the derivative of f with respect to x?
3x squared minus 4x.
Perfect. Left siders, you tell me the derivative of f with respect to y, if you would. That was easy. Love those ones. That one's nice. Quick hit if you're okay with doing the pieces so far. So what we've done, we've done this. We found the partial of f with respect to x and with respect to y. We also have found the unit vector. Can you all tell me right now, what is u sub 1? What's the x component of the unit vector? What is it? What's the y component of the unit vector? Let's put it together. So if I want to find the directional derivative in the direction of u, we take the partial with respect to x. We mash it together with that thing, that u sub 1, that should be a number. All right, that's a specific component to a specific vector. It should be a number. It shouldn't have x's and y's in it right now. Okay, it should just be that root 3 over 2. Then we take the partial with respect to y, that's our 3y squared. We mash that together with the y component, or the second component, or whatever matches up with this, of that unit vector. Okay, truly, don't be like, yeah, I get it. Truly, do you understand it? Show of hands if you do understand where all that stuff comes from. Now, I want you to notice a few things about it. And we're going to write some of the stuff out later, but I want you to notice a few things about it. Do you see any i's or j's or anything at all? Is this thing a vector? No. It's a scalar function. What a scalar function means, you plug in numbers, you get out a number. That's what a scalar function is. It's a scalar function because it's given you what? You need to know what this is. What is this thing? What is it? It's a slope of tangent.
Plane?
No. Planes don't have slopes. Imagine any plane, infinite number of slopes. Planes have normals. Oh, that's the next section. This is the slope of a tangent line to a... Do you know I cry myself to sleep sometimes?
Yeah.
For moments like this. When I have you go on, we do all this stuff, and you go, do you know? I know you know. What's a derivative freaking give you, like always? Slope of a tangent line to a whatever this thing is. Whatever that is. What is this? It's a surface, but only in the direction of that unit vector. And not that you understand. Listen, if that's the slope of a tangent line, it's got to be a number. You already have a vector that's saying it's in that direction. You already have that. Slope is a number. That means it's a scalar function. It is not a vector function. Should you understand that concept? That's a big deal. So I'm going to write that out. Right now, what this is the equation for the slope of the tangent line to this f of xy surface at any point. Look. Any point. Plug in x, plug in y. Any point. But only in the direction of what vector? Only in the direction of u, right now. That's what it's giving you. Can you please write that out? This is the equation for the slope of the tangent line to this surface at any point, but only in the direction of u. Now let's go back just a little bit. So we know that we're finding this. You need to know what that thing is, what a derivative always is. A slope of the tangent line, well, a derivative of a function in a direction of a vector is a slope of a tangent line. If you remember from last time, we created this plane. It was parallel to the u vector, created a curve on the surface. I'm not going to go through it all that much, but we created a tangent line to that curve that was created on the surface. Make sense? It's a tangent line to a surface, but it's only in the direction of whatever vector I give you. Find your partials, find that vector. I have to give it to you, and then put this stuff together. So we've done that. What we've done is created the equation for the tangent line, equation for the slope of the tangent line to that surface at any point, but only in the direction of that unit vector. And now if you're okay with that one. Now, how do we find a specific slope to a specific point in that direction? Well, if this is to any point along that vector, so right above that vector or parallel to it, it's any point. Do we have a certain point that I want to find the slope of the tangent line to the surface in this direction at that point? Man, it's a mouthful. But can we do it? Do we have a point now? Yeah. So given a function and a unit vector, you can always find this. But to figure out a specific slope, just like in Calc 1, a specific slope requires a specific point. Does that make sense? This right here, what I'm giving you is essentially like giving you the x value for an f of x, like a derivative, first derivative of f of x. And you plug in x, right? Well, now you get to plug in x and y, and you find the slope. Can you please do that? Find the derivative at that point. What number are you plugging in for x, please?
1.
What number are you plugging in for y?
2.
What number are you plugging in for u sub 1?
You already have.
You're not.
It's already
You already have it. Don't worry about it. It's already there. I had to give you that vector. Just trying to trick you a little bit. That's what teachers do, right? Just throw out trick questions. Right? That's how mine did.
Well, you erased it. Sorry.
Yeah, that's where we're at. It doesn't have to be pretty. This thing's not pretty. I think I simplified this and got 6 minus root 3 over 2. Did you get the same thing I got? But never lose track of what it is that we're actually doing here. What is this? Firstly, is this a vector? Yes or no? Is this a number?
Yeah.
What does that number mean? Come on, put it all together. What's that number mean? This is a slope of the tangent line to
the surface.
that surface. Way to go. That surface at
The point 1 point.
that point in this direction. Basically saying, cut the surface, find a curve, find the tangent line. This is the slope of that tangent line at that point. Of course, on that curve, you're going to have different slopes, different tangent lines. At that point, on that surface, in the direction of that vector, that's the slope that we find for the tangent line. Does that make sense?
Yes.
Now, to figure out, yeah, okay, we're good. That's what we're doing. Do I need to write that, or is that pretty much clear for you? So this statement pretty much says it all. So the only thing you would change for what this is the slope of the tangent line to that surface at that particular point, but only in the direction of that specific unit vector. Show of hands if you fully understand that. Fully. You sure? Any comments, questions, or anything before we continue? Okay, I'm going to change this a little bit. This is a little, not really advanced, but I'm giving you that, and it's a little weird, okay? So let's see if we can change it a little bit, and I can hammer out 2 birds with 1 stone. What happens if I say I don't want a specific angle? Because that's not actually very common. But I tell you, I want this, so derivative of this at a point in the direction of the vector, and I want you to see how the problem changes. That. Now let's go through it. Let's see what changes. Let's see what doesn't change. Okay. Firstly, am I giving you an angle here? No. Don't. That you're working too hard if you try to find the angle with the x-axis. Okay, you're working way too hard. Don't do that. It's easier. What 2 things do I still need for a derivative, a directional derivative? Do I still need a point?
Yes.
Do I still have a point?
Yes.
What else do I need?
Unit vector.
Wait, be specific. Do I need a vector or a unit vector? A unit vector. That's important. Have I given you a unit vector?
Yes.
Ah, no. How do you know if that's a unit vector? What would you do? Find the magnitude, which is not a waste of time. Because if the magnitude is not 1, you have to find the magnitude anyway to find the unit vector. Does that make sense?
Yeah.
Now I'll tell you right now, that's not a unit vector. That's not even close. So you always need a point and a unit vector. I can give you the angle. That's actually pretty easy. Or I can give you another vector. Just don't make the mistake of taking this number and putting it here, because this is not a unit vector and you have to have one. Does that make sense? Can you do me a favor here? Since I'm not giving you this, this is irrelevant for this problem. This is not irrelevant, you need it anyway. But can you take some time and find me the unit vector I need for that? Go for it. A unit vector is always found by taking the vector I give you, or the vector you find, and dividing it by magnitude. That's what a unit vector is. So we have this 2 root 3I plus 2j over the magnitude of this. Explain in your own words how you find magnitude of any vector.
Square root out of square root.
Good enough. Square them, add them, square root them. If you simplify them, which you should, that becomes your unit vector. Yeah, I know. I gave you did you notice I gave you the same one twice? I gave you the same thing. So the point of me doing that is to say, listen, I give it to you two ways. I can give you an angle and say find the unit vector, or I can give you a different vector. This was a good example for you though. It says don't just take these components and plug them in. You literally have to find the unit vector. But no matter what, as soon as you do it, as soon as you get that unit vector, however you can, the work is all the same. Find your partial derivatives, put your x components with your x derivative, y components with your y derivative, and you have the formula for the equation, or the equation for the slope of the tangent line to the curve at any point along that unit vector. Then the specific point, we get the same exact answer. Ladies and gentlemen, are you guys okay with finding the unit vector and using these things in those spots? Show of hands if you are. Okay, now there's something really, really interesting about this. If you take a look at it from here, you might have noticed this, but this is pretty cool. It's really convenient for this technique. But I want to show you something. Do you notice how that's a partial derivative with respect to x, and this just happens to be the x component of a vector? That's the partial derivative with respect to y, and that just happens to be the y component of a vector. And if I want to do x, y, z, I could just have the partial derivative with respect to z and the z component of the vector, the unit vector that we have. Well, that's interesting. Now I want to see if you guys can put it together. This comes from a vector, yeah? What thing in vectors takes some pieces, multiplies them together so that you have the x's and the y's and the z's, and then adds them up, giving you not a vector, but giving you a scalar? What does that? Dot product does. Let's run with that. Let's just pretend that this actually comes from a vector, from a dot product of a vector. It looks a lot like a dot product. So, well, how do I want to do that? Yeah, I guess I just straight from here. If it's a dot product, if it is, stick with this. This is pretty cool. You're going to get something you don't even know. You don't even know yet. But we're going to get something pretty cool that you have used already in your other classes. I guarantee you've used it because I talked to some of you today about it. If this is my second vector, this one's the easy one. This would be u sub 1I, the x component along the I direction. U sub 2j, the u component, the y component along the y direction. Head nodded, you okay with that one? It's not a coincidence that we have exactly what a unit vector is, because that's literally what we have. We have a unit vector out of that thing. So right now I know that this piece, that's just our unit vector. Does that make sense? Now, in order to get a dot product, think back to dot product, okay? It's 11.3, I think. Think back to dot product. In order to get a dot product, you must dot a vector with another vector, because the i's have to match up, j's have to match up, okay? And you eliminate the vector, you get a scalar out of it. So that means that if I'm dotting this, if I remove the u sub 1, I just have that partial with respect to x. But that's got to be the I component there. That's got to be the x component. Does that make sense to you? If this is a vector, it's got to have an I, and it's got to have the x component match up with the other x component. That. That's got to be the j component. It's got to match up with the other j component. Let's verify this for me. Let's make sure the dot product actually works. Check it out. If I do the dot product, we take x components, multiply them. Y components, multiply them, and add the result, getting a non-vector, just a scalar function, which is what derivatives are. So hands feel okay with that one. So what we get is, we clearly get the unit vector, we get the direction vector, but then we get this weird vector. Like, what is that? Well, let's verify something. Some really key points I'm going to write out in a minute. Number one, is this thing actually a vector?
Yes.
Yeah, that's a number or a scalar function giving you a numbers. Makes sense? I plus another scalar function giving you numbers, j. You follow me? That's a vector. Okay, cool. Is this vector in 2 dimensions? Is this vector in 2 dimensions?
Yes.
Giving you a derivative that's the slope of the tangent line in 3 dimensions. That's really interesting. But this is some weird vector. Here's the deal. What we do with this weird vector, we call it a certain name. We call this weird vector the gradient. You have probably heard of the gradient in some of your other classes, but that is what the gradient is. So this weird vector, the gradient. Call that weird vector the gradient. There's a little bit of notation that we have. I need to show it to you. Here's how the gradient looks. It's this reverse delta. Looks just like a delta, but it's upside down. So reverse delta, we call it del or gradient. It's not delta. Delta x, delta y, that's different than this. Okay, so we say del f or gradient of f. Are you guys clear on that one? Let's practice both. Let's say gradient of f
Gradient of f.
and del f.
Del f.
Yeah. The gradient of a function is defined as that weird vector. This is no longer called the weird vector, right? It's the gradient of that function, or it's del f. That is the gradient. Is it hard to find? Do you know how to do partial derivatives? That is not hard to find. But that changes some stuff then. So track with me here. We spent a lot of time proving this. This one looks a lot less, so here's your 20-second recap, okay? We spent a lot of time proving this last time. But this one looks a lot like a dot product. If I call this a vector, and this is clearly a vector, then this thing, if I redefine it, say, let's call that something so I can make my work easier. Let's call that a gradient. Cool. Is it a vector? Clearly. Is that a vector? Clearly. Dot product of 2 vectors gives you a scalar function. That's a derivative. So okay, let's redefine that as del f. And now we have this brand new thing that we do as our derivative. Okay, our derivative then can be redefined as this. That's it. Del f, gradient of f. And typically we do put the xy dot u. Did you guys understand that? It's not even. It is a proof, I guess, but we're defining the vector, so it's kind of a weak proof. But do you understand that this would literally give you back that exact same thing every single time? This is typically what we do. This is how we find derivatives from now on. This is practically the same thing, but we make it easier, and we talk a lot about what the gradient does for us coming up here real fast, what that really is. So this is what we typically do. The steps are usually find the gradient, plug in the point, find the unit vector, dot product, and it's that easy. It goes very, very quickly. Do you guys understand down to this point? Show hands if you do. Okay, that's fantastic. I'd like to write out a whole bunch of notes. We're going to get real serious about what the derivative is. We're going to get real serious about what the gradient is. I want to make sure you understand the concept fully before you go any further. Are there any questions so far, or has this been explained pretty well? You guys okay with it? Okay, so let's put this all together. So some pretty major notes. The first one, the derivative. Is the derivative a vector?
No.
The derivative is a,
Scalar.
and it represents the
Slope.
slope. So derivative is a slope, it's not a vector, it's a scalar. How about this one? What is del f? What's the gradient of f? Is that a vector?
Yeah.
Absolutely. Is del f the entire derivative? Is that what it is? No, it's part of it. It's part of it that we dot product with the unit vector to get the derivative. So this is part of du. Our directional derivative. Here's how I want you to think about this. Then I'm going to give you the properties and I'm going to prove them. I'm going to prove my statements here. Here's how I want you to think about the gradient. What the gradient does, it's clearly a vector, but it gives you the gradient, it gives you the vector of the climb of the surface. That's how I want you to think about it. The gradient, keyword there is grade. It gives you the rate of climb, or the vector for the rate of climb of your surface, and we're going to talk about that. So right now the statement I want you to make is the gradient refers to the grade of your surface. Grade like you're going up a hill, right? That sort of grade. That's what it relates to. Grade, climb of your surface. Now, we've already did an example, so I'm not going to write this part out, but you should know to find a specific grade, a specific climb, you need a specific point and a specific unit vector to give you that direction. Does that make sense? So this would give you the overall, what the climb is of your surface, and we'll talk about how exactly it does that. But to find a specific one, we got to have a direction u, and you got to have unit vector, and you got to have a specific point. Does that make sense to you? Would you want me to write that down? Would that be helpful for you? Okay, I'll write it down. Let's talk about some properties. I'm going to prove the ones for you that need proving. First one's really obvious. I'm not going to prove it. If your gradient equals 0, the derivative equals 0. Is that clear? You can prove it. If you have a 0 vector here, 0 vector dotted with any vector, I don't care what it is going to be 0. So if if the gradient equals the 0 vector, then your derivative is 0. Oh, yes, that was a proof. If the gradient of a function is 0, then the derivative of that function is 0. Done. For any unit vector. kind of obvious from the dot product. This one's not obvious. I'm going to spend some time on this one. This is the two big punchlines we get out of this. All right, I'm going to draw hopefully a cool picture that's going to illustrate it. This is a really cool one. It's not intuitive at first. Here's what I'm going to say. Can you imagine a surface and this curve going along it in the direction of this unit vector and putting a point right here and taking a tangent line? It's going to have a slope, right? Somewhere along there, we should be getting a maximum slope of that curve. Does that make sense? Somewhere along the surface, we should have a maximum slope on that surface. Actually, is what we should have. The maximum slope of a surface occurs. Actually, let's say the value. The value of the maximum slope of the surface is the magnitude of del f. It's the magnitude of the gradient. I'm going to prove it to you right now. So that's not intuitive. You're like, well, what do you mean? What are you talking about there? I'll prove it. Watch. Just to put it in perspective, okay, just so you get the context here. Ladies and gentlemen, what does that represent? What is this, please? Come on, quickly. What is that one? No, this is not del f. That's a derivative. What's this mean? Slope of the tangent line to a surface in some direction. Makes sense? That's what that means. This is going to have its max value. So I'm saying, here's the max slope. This is weird, all right? Here's the max slope of your surface, not in any direction, well, it's going to give you a specific direction, but of the surface. What's the maximum slope that we get on our surface here? You guys getting what the idea here? Has a value of this. And this will happen only when this happens. Only when the unit vector is c times del f, where c is a scalar. Write it down, and I don't want to talk over you. You write stuff down. So write it down. I want to talk about that one, and then I'll prove it. It's not a hard proof. You'll clearly follow it. You guys okay with it so far? Got it written down is what I mean? Are you okay with that? I don't know. I'm going to prove it in a second. Here's the main points about this one. Check it out. Is that a vector?
Yes.
Is that a vector?
No. See?
C? No. Is that a vector?
Yes.
C? Yes. Vector?
Yes.
Come on, is gradient a vector?
Yes.
That's how we made it. Tell me something. If a vector is equal to a scalar times another vector, what's it mean about these two vectors?
Parallel.
Parallel means they have the same unit vector, clearly, but it also means they're in the same direction. Does that make sense? Here's the whole statement then. I'm going to prove it in a second. It's not a hard proof. It says, hey, tell you what, this is going to have its maximum value when the unit vector is going the same direction as the gradient vector. That's when you're going to get the maximum slope of your surface. That's what this says in English. Derivative slope, slope of a tangent line to a surface, slope of a surface. Let's think about it that way. The slope of the surface has its max value when this is going the same, when the unit vector is going the same direction, scalar multiple, same direction, parallel, same direction, scalar multiple as your gradient vector. That's when you're going to have the maximum slope. Does that make sense to you? Show of hands if it does. So this whole thing means unit vector and the gradient are in the same direction. You need to stick with the proofs. I know they're dry. I get it, but I really want you to understand it, okay? Don't just rip through this. The math is going to be easy, but I want you to get the idea behind this. So I'm going to prove this here real quick for you. So check this out. Just stick with it. Here's how we're going to start. If our derivative of a function in two variables is equal to del f dot u, which it is, that's literally how we defined it. Here's the magic. You ready? Here's the magic. Check it out. We also know some stuff about a dot product. You guys need to focus. You also know some stuff. Right? No? Okay. Let's try that again. We also know some stuff about a dot product. Namely, we know that whenever I take a dot product of two vectors, verify these two things are vectors.
Yes.
We can also do it this way. We can take the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. Do you remember that? Is that somewhere in your memory banks back there?
Yeah.
That is also the definition of a dot product. But wait a second, let's think about this. So then our derivative could equal this stuff. Now let's talk about it. Let's talk about it. Everyone in class right now, what type of a vector is U?
Vector.
What's the magnitude of a unit vector?
1.
Oh, crazy. Now, let's think about this. Since we've just proven that the value of our derivative is the magnitude of the gradient times the cosine of the angle between them. Think about this for a second. Think about this for a second. Think about this for a second. When does this has its maximum value when this side has its maximum value, correct? What's the maximum value that cosine actually attains?
1.
Maximum value of cosine is 1. What's the minimum value of cosine?
-1.
-1. We're going to talk about that in property number 3, okay? It's going to be very similar. We're going to refer back to this. But the max value that can have is 1. Where? What gives you 1? Cosine of what angle gives you 1? So this says this. The angle, the maximum value here is 1. Got it? That happens when the angle is 0. That happens when the angle between the two vectors, that's what that means, the angle between these two vectors is that theta. It says the maximum value, which is 1, happens when the angle between these two vectors is 0. That means they're going the same direction. That means they're parallel. That's proving this case. So the max value for cosine is 1, and it happens when theta is 0. That says they have to be going the same direction. Max value of cosine is 1 when theta is 0, and that says that the angle between del f and u is 0. That says that they are parallel. That says they're in the same direction. Do you guys want a little recap of that? Or could you follow it? You couldn't follow it? Or you could follow it? Those two questions I asked at the same time, you're like, this, I don't know anymore. Do I know anything? Well, yeah, you're in Calc 3, you know a lot. Okay, you guys are smart people. So don't scoff, you are. You really are. To make it here, it's no joke. It's a hard road that you've gone down to make it here. So first property, it doesn't need to be said, but this is an important one. The maximum value of the slope of a surface, what? Yeah, crazy, happens at that value. What direction does it happen in? That direction happens in that direction. It happens when you go del F and U have to be in the same direction. Why? Well, because we can define a dot product this way. That is 1. Cosine theta, this maximum value is 1. Happens when you have an angle of 0. When the angle between these two vectors is 0. When the angle between these two vectors is 0, we have things that are parallel. They're going in the same direction. The maximum value of your derivative happens when your unit vector is parallel or same direction as your gradient vector. That's when we get the maximum slope of a surface. Should you understand the concept there? Any other theta, if I put anything else here besides 0, it's going to create a value less than 1. A value less than 1 is a fraction less than 1. A fraction less than 1 takes a piece of that. So basically, I want you to think about it this way. You're going to have this direction, the direction, that del F, that's giving you a vector on 2D, okay? It's giving you the direction for the steepest slope. What the U does, if it's going in the same direction, you're getting the steepest slope. If it's off a little bit, it's taking a fraction of that steepest slope. It's basically turning it and getting something less steep. Do you see my point on that one? If the angle between there is anything else besides 0, if they go in different directions, you're taking a literally, you're taking a fraction of that maximum value. That's what you're doing. How about this one? This would be crazy. Since we already accomplished this one, proved it. That's the max value. When's the derivative going to have the minimum value? What do you think? What's the minimum value going to be? Well, let's go back over here. What's the minimum value of cosine, everybody? What's the minimum value of cosine?
-1.
When's that happen?
When it's on
Pi. When it's on pi. Well, okay, so wait. When the angle between two vectors is pi, can you picture two vectors right now? If these are two vectors and the angle between them is 0, they're going the same direction. If the angle between them is pi, they're going opposite directions. That's basically the same direction with a negative. That's the idea. Does it now wait? Does it make sense to you? This is a very logical statement here. It should make sense to you. Look, if the steepest way up a slope is this way, the steepest way down a slope is the other way. That's all it's saying. That's literally all it's saying. So we're going to state that one, and it just happens when the angle is pi. That's just the opposite of that first vector, the del x. Yeah, so basically just see the previous problem. The theta has to be pi. That gives you -1 for cosine of pi, and that puts you the steepest way down. That's the minimum value. That is the smallest, the lowest slope, the most negative slope we get. So a little bit of a recap, then I'll make our final statement. I'll give you a pretty cool picture on how it relates to what you've learned so far, and we'll move on. So the whole deal says this. When we're trying to find our derivative, it's going to have its maximum value at the magnitude of that gradient. Why is it going to have that? Because when we look at how the derivative is found, the directional derivative is found, it's a dot product. And the angle between those two vectors, this vector and that vector, has to be 0. Which means that to get the maximum slope of our surface, we need to put our unit vector in the direction of our gradient vector. That will give us max slope. Any other vector besides that specific vector is going to take a fraction of our gradient. That's what's going to happen. It's going to take a fraction of our gradient, making the derivative less steep. Until we get back down to pi, which gives you -1, and that's this magnitude-wise, that's absolute value-wise, that's the same slope, it's just in the opposite direction. Does that make sense to you? So what the gradient gives us, so all this says is that the gradient gives us the vector let me repeat that. The gradient gives us the vector for the steepest climb up a surface. That's what it's giving. Does that make sense? If u is not in the direction of that vector, that gradient vector, then you're basically turning off, taking a fraction of, turning off of the steepest climb. So if you understand the concept, that's what it's giving you, that's what a gradient actually is. When you're using the gradient in the classes, that's what it's really representing. Use it for a whole lot of stuff. We're going to use it in vector fields. We're going to talk about a whole bunch of things with this gradient, but right now it starts with this concept. I'm going to show you. Let's take our surface here, and let's take this point right there. Here's what happens. What happens is the gradient is going to give us the vector on 2D that says, hey, look, line up your tangent line so that it's literally right above that vector and going through that point, or parallel to that vector. Listen carefully. Parallel to that vector, so that would be the u. The u would be parallel, a scalar, where did I put it? A scalar multiple of that vector. So you okay, well, here's our gradient, line it up so that my tangent vector is right on top of that, or at least going parallel to that. And what's going to happen with this is the slope going up that surface at that point will be the maximum slope that you have going through that point. That's what the gradient vector tells you. It gives you the vector for the steepest grade of a surface at a point. I'm not getting a lot. You should be excited about this one, but I at least want something more than dead silence. You'd be like, nah. Do you understand it?
Yeah.
Do you understand that the gradient's not a 3D vector? That's a big deal. Gradient's a 2D vector. The gradient is one dimension lower than the function. That's a big freaking deal. We deal with it in the next section, okay? The gradient is 1 degree, 1 dimension, 1 step down. I don't care how you think about it. It's 1 dimension lower than the function itself. This function is here. That's 3D. The gradient is 2D. If we had a 4D, the gradient would be in 3D. We're going to use that in the next section. It's a big deal. Now I'm gonna talk about this one too. So if you wanted to go the steepest way down the hill, so drop down the hill fastest, can you see that all we'd be doing is changing this around and taking negative del f? That's what that's doing. If del f gives me my 2D vector that I want to put my tangent line right over, or at least parallel to, that's giving me my steepest climb. If I want to go back down the hill, I just switch it around. Make it negative del f, that's giving me my steepest climb down the hill. Head nod if you understand that one. What u does, think of u, if u is anything else besides parallel to delta v, or sorry, delta v. If u is anything else besides parallel to del f, the gradient of f, it's turning off of that path. It's taking a fraction of this and turning off of that path. That's how I think about it. It works really well for me. This idea says, hey, yeah, del f gives a vector for the steepest grade. Cool. If the unit vector that I give you is not parallel to that, it's not a scalar multiple, it's not in the same direction, it's basically taking this vector, which is given the path of steepest climb, the steepest rate of change of the surface at a point, and saying, nah, I don't want to go that way. I want to go a different way. Well, if that's the steepest and you go a different way, then you're not going the steepest. You're going less steep than that. Does that make sense? It's turning away from that steepest path. It's turning away from the rate of steepest climb, or the direction of the steepest climb. It's turning away from delta f, or del f. Sorry, it's easy to say delta, isn't it? It's turning away from the gradient of f. Head nod if you understand the concept on that one. I want to do one example, then we're going to take our break because I want to make sure that you see it. We have spent a whole long time talking about the properties, doing all this stuff. The actual doing the processes, honestly, not that hard. You can see it right here. Finding del f is easy. Finding unit vectors, really easy. Put them together, it's a dot product. Can you guys do partial derivatives, find unit vectors, and do a dot product? Yeah. Then let's try one right now at least. You have questions? No? Okay, we're going to try that. Honestly, I'm going to work as fast as I can through the derivatives. We're not going to waste a whole lot of time doing partial derivatives. We're here for the process of how you take the gradient, use it with the unit vector, giving you a direction, and finding a directional derivative. That's the process here, not trying to reteach you derivatives every single day. That's we don't have time for that. So first thing, if you're going to find del f, or the gradient of f, what two things do you have to do in this case? What do you have to find first? Partial derivative. Okay, so yeah, because this thing is based on partial derivatives, can you please go ahead and find me the partial derivatives right now? Go for it. If you don't want to, if you feel comfortable with finding your derivatives on your own, I'm going to give you about 10 seconds or so per derivative, and then I'm just going to write on the board. You can practice them later, or if you feel real comfortable, that's fine. You can just wait for them if you'd like. It's one time I'll tell you to do that. Negative? Yeah, negative. Those right there are the partials. You got negative to the chain rule, bring it up, you have partial derivatives there. Let's go ahead, since we found partial derivatives of x and y, we can now make our gradient. What's the first piece that you write for your gradient? Is it a partial of x or partial with respect to y?
Partial of x.
Okay, we need something right after that. Come on, everybody, what do you need right after that? Keep in mind that del f is a vector. What do you need right after that? I. You all right with it? Are you all right with the math behind finding it? Now, what is it? What is this thing? Is it a vector?
Yes.
What does that vector give you?
The steepest grade.
The steepest climb up that surface, whatever it is, at any point. Make sense? That's pretty cool. This is the vector that will give you the direction, the steepest climb of that surface at any point. You might want to write that down. This is the vector that gives you the direction of the rate of maximum slope of that surface at any point.
Is each number supposed to be squared?
Yeah.
Oh. Might make a difference.
I wasn't going to say anything.
You should say something. I was just going so fast.
Yeah.
Don't be like, let's say what? Do as I do. What is that one? Do as I say.
Not as I do.
Yeah, right. Don't make mistakes. Max the envelope. What other trite comments can I make about this one? I don't know. Lost it. So, yeah, thanks. That right there, that gives you the vector, the direction for the maximum slope of your surface at any point. In other words, here it is. It's where your tangent line should be aimed if you want the maximum slope. Do you get that? That direction is where your tangent line should be aimed if you want the maximum slope. Does that terminology fit well with you? Can you understand that concept? Where you should aim it. Now, let's find it at that specific point. Good thing you didn't forget to square it like poor old Leonard. Ladies and gentlemen, is this a slope? I know I'm hammering it down, but I want to make sure I do. Is that a slope? Is this a slope?
No.
What is it?
It's a vector.
It's a vector. It can't be a slope. It's on 2D. And your surface is 3D. Can't be a slope. That's not a slope. What is it? This is the vector that is giving you the direction that you need to put your tangent line to get the maximum slope of that surface through that point. I'll say that one more time, it needs to sink in. This is the vector on 2D, on your XY plane. It's this vector that's giving you the direction so that you need to point your tangent line parallel to that on your surface to give you the maximum slope of that surface through that point. It's just the direction you need to aim your tangent line. Make sense? Next, what we're going to do. So this is step one, okay? You find this, you plug it in. If that's your direction of your maximum slope, and I give you any other vector, unit vector, if I give you that, we dot product those things, we find our slope. That's the next step to this. Have I made it make sense up to this point? Do you understand what a gradient actually is? Do you understand that it's not the slope? It's the direction on one dimension lower than your surface, whatever you have, that gives you the direction to put your tangent line so that you get the maximum slope. And if I don't go in that direction, I get less than the maximum slope. Show of hands if you understand that concept. That's a big deal. So we're going to talk about a couple more examples next time when we come back, and we're going to make our way through it. Okay, so now it's some time for some pretty quick examples. Again, our goal here, it's not to relearn derivatives. It's to put the idea of partial derivatives together with this new idea of a gradient vector and see how that relates. So the first thing I want to tell you is that the idea of a gradient vector can be extrapolated. You can do that previous proof really quickly with three components. It's not bad. So what I want to tell you is the gradient on three components a vector in three independent variables is not any different than the gradient in two. You just take all the partial derivatives, put them with I, j, k, however many components you have. So for us here, if I want to figure out the gradient for this at that certain point, this says find the gradient and plug in that point, x, y, z. Well, if we do, any gradient ever takes all partial derivatives, so x, y, z. In our case, we get z minus y. So low d high minus high d low, square the bottom way we go, because our independent variable here is x. That's what we're not holding constant. Y and z are held constant. And square the bottom. That right there is the partial derivative with respect to x. I know I had some of y'all work on that on your own. Did you get that on your own? If you didn't, you should be retrying this on your own at some point later, okay? That's what you should be doing, all this stuff. I told you during a little break, I'm just going to basically give you answers for partial derivatives. We're past that. So if you're doing this now, or if you're watching this later at a different time, stop this and do these pieces on your own. You need to be able to do it. I just don't have time to do them with you right now. Is that clear enough for you? Okay. So this guy, that one's actually pretty clear with respect to y. That's not bad. And this guy is that. That's what those parcels are. I leave that negative out front so we can just subtract that vector component. So when I put it together, if this is the partial with respect to x and y and z respectively, my gradient says you take the partial with respect to x, and what that scalar function, which a scalar function does, is the x component of this vector function that we get. This is the y component of the vector function. This is the z component. Of that vector function. That right there is the gradient. Quick head nod if you're okay. I don't know if you're okay on the derivatives, but given the derivatives, are you okay on finding the actual gradient? Yes or no? Now from there it says, hey, you know what? Any gradient you can plug a point into. Any gradient can give you that. It'll give you the direction of the steepest slope of whatever this thing is. So let's go ahead and plug in some numbers here. If we do, just mind your x, y's, and z's. Just plugging in numbers. And then if we simplify this, I want you guys to check my work, maybe on your own or something. I got 1/16 I plus 1/4 j minus 3/16 k. Is that what you all got? I said 3/16, right?
Oh, yeah.
I know that was really quick, but that's just the idea of using the gradient with 3 variables. Head nod if you're okay with the idea behind that. It doesn't really change. Find your partials, put them I, j, k, whatever, and that is now your gradient vector. Now I want to move on. I want to move on past the gradient. I want to use it to start finding actual slopes, finding derivatives, finding slopes of tangents to surfaces. We're going to start that on that example. So let's do that. I'm going to do it step by step though. Here's how, from now on, I want us to be finding our derivatives. The first thing I want you to do, anytime I say, hey, find the derivative, find the slope of the tangent to a surface in that direction, at that point, here's your steps. Step number 1, find the gradient. Step number 1, find the gradient and plug in the point. It ain't going to change. Find the gradient, plug in the point. So our number 1 here, find the gradient at the point. What I want to figure out right now, so this is what we do all the time, find the gradient at the point. Specifically, I want to find the gradient of f at the point 2, 2. That's why we did that example right now. Say, hey, how do you find that? Well, you find the gradient first and then plug in your point. I'm going to give you about a minute because this one's kind of, well, a couple minutes. Shoot, well, maybe we'll do it together. In order to find the gradient, what must you be able to do? So our partial derivatives are with respect to x and with respect to y. That's only 2 we got. If we do it, yeah, we're going to take a lot of shortcuts on these derivatives, all right? Here's what's going to happen. If we take a lot of shortcuts with respect to x, that's my only independent. Everything else is held constant. That means when I get to do the chain rule, I get a 2x out of it. Do you see it? But the 1/2 you bring down is going to get rid of the 2. So what we end up getting is x over square root drops -1/2 power x squared plus y squared plus 1. That right there is the partial derivative of f with respect to x. Can you follow that? With that in mind, can you give me the y? What do you think it's going to be?
Y over.
Hey, provided you can do that, provided you can actually find those things, can you make the gradient up for me right now? Do it from here. So I'm giving these to you right now, okay? From here, make the gradient up, please. Bless you. What do I start with, by the way, to make my gradient? Come on, left-siders, what do I start with? Let's get more participation than we've had today. What do we get?
Partial perspective.
Got it. What else?
I.
Good, because you need to know it's a vector. Then what? Right-siders, come on. And that right there is the gradient. You are done with the gradient. Head down if you're okay with that one. Are you done with step 1? No. What I want you to do, what the process is here, find the gradient, literally plug the number in. Okay, that's what I want you to do. Plug the number in, figure out that vector, figure out the unit vector, and then dot product them. So dot product 2 actual specific vectors, that's a lot easier than dot producting first and then plugging numbers into a big function. Does that make sense? So figure this out first, this del f, or gradient of f at the point 2, 2. Did you find it?
Yes.
2/3?
Yes.
What is it? Don't just say gradient. I know it's a gradient. What is it?
It's a vector.
Direction, which means vector of the
Slope. Well, the
steepest slope of that surface through that point. Well, kind of in the direction it would give you through that point. That's the direction for the steepest slope. You with me? If u is anything else but a parallel vector to that, then what we would get right now is something that's not the steepest slope. If I wanted to figure out, please listen carefully right now, if I wanted to figure out the steepest slope through that point, all I would have to do is what?
Dot it parallel u.
I wouldn't even have to do that. Say it in the back. Magnitude. Since the steepest slope is the magnitude of your gradient. If you find your gradient vector through a point, take the magnitude, that is the steepest slope. That is what it is. And not that you understand that concept. That was the whole proof. That we took like an hour talking about that. That was the point of what a gradient is. That is the direction of the steepest slope. If I take the magnitude of it, it literally gives the scalar steepest slope of that surface through that point. You with me? So, and when we're finding our derivatives, we go, okay, we're going along a different vector. Step 1, find the gradient, no problem. Plug in a point, no problem. You have it. Step number 2, you also need what type of vector to do this. Come on, what type of vector?
Unit vector.
Do I have a unit vector? Can you
no.
find a unit vector?
Yeah.
That's step 2. I'm going to give you about 10 seconds. Find me a unit vector. It's an easy one. Three, four, five right triangle. Hey, quick question. Is this a scalar multiple of that? Is this a scalar multiple of that? Is that a scalar multiple of that? Can you multiply 2/3 by something and get 3/5? Yeah, me neither. So no. So what we're getting finding, you need to know what this is. Don't just do math for the sake of math. That sucks, all right? You're going to be finding the slope of the tangent line to that surface at that point in that direction. That's what we're finding. We found the unit vector. It's the same direction as that. Is it the same direction as this? No, because it's not a scalar multiple. So what we're going to be finding is not the steepest slope, but the slope of the tangent line to that surface at that point in that direction. So this is step 1, find the gradient at the value. No problem. Step 2, really easy. Find the unit vector. Whatever I give you, just find the unit vector. You got it. You with me? What do you suppose step 3 is? Think back to what the derivative, we defined it. We spent the first 20 minutes doing that. What's the... Oops. So step 1, gradient at a point. Step 2, unit vector. No problem. Step 3, dot product. So right now I want you performing the dot product, please. Let's see, so got this part, that's this. Got this part, that's here. So all I need to do is dot product this vector and that vector, and I'm done. Dot product gives me a scalar, which is a slope of the tangent line to the surface at the point, but in that direction. That's what we're doing. It's like a dance. It's like a magical little dance that we're doing. Math magic. Have you done that? Have you dot product these two vectors and got something?
Yeah.
What, 6/15ths, 8/15ths? How much you get out of that? 14/15ths? Vector? What is it?
Scale.
Slope, scalar, scalar slope. This is the slope. I know I've said it 4 times, but that's the slope of the tangent line to that surface in that direction at that point, through that point. Show of hands if you feel okay with that one. That's the idea. That is what we're doing. By the way, you can, if you're not given a specific point, if you weren't given that, and you stop right here, you could still do a dot product, couldn't you? With just that specific unit vector that we get right there, you could still do it and figure out the derivative at any point, but only in the direction of that unit vector. Does that make sense? We could do that. In fact, our first example today, when we started this whole thing, we literally did that. We said, all right, that was the function, the equation for the slope. That we spent like 20 minutes doing that. But that's the same idea. It's basically what we did earlier, first example. By the way, what if you are not given a vector? What if you're given 2 points? Could you still do it?
Yes.
How?
Combine or create a vector.
Let's do that. Let's try one of those real quick here. You know what? We'll do 2 of them. What's your steps? If I ask you for the derivative, what's the first thing you're doing right now? What is it?
Find the vector.
What vector?
Between the
Step 1?
gradient.
Oh dear. Okay. Come on. Let's all practice this together like we know what we're doing. It's got kind of weird. All right. Listen, your derivative is literally just 2 freaking things. What 2 things are you dot producting? The gradient and the. Which one do you find first?
Gradient.
Gradient, just because you have the function right there. Let's find the gradient. So can you please right now find the gradient? What? By the way, to find the gradient, you actually need a point. What is our point that we're going to be using here? What's the point? Please don't use the wrong point. Please use the correct point. It's at that point. So I'm going to give you just, a couple minutes, maybe like 1 minute. Can you please find the gradient, plug in the correct point, and give me the actual vector? Should be just numbers in there. No x's, no y's. Hey, have you all been able to find the gradient vector for that?
Yes.
Did you plug in the point?
Yes.
So step number one, if we want to do this step by step, first thing we do is find the gradient of f of whatever the function it is. So that's with respect to x first, I, plus respect to y, j. Can I get a double check on that if you get the same thing? That's the gradient. What it is, well, path of the direction for the path of the steepest climb. That's what it is. At a specific point, we got to plug in a specific point. So if we want to find this at the point 2, 0, which is that's what it says. Plug in 2, plug in 0. Plug in 2 for x, plug in 0 for y. If we plug in 0 for y, we get I. Plug in 2 for x and 0 for y, we get minus 2j. Can I get a double check on that one? I minus 2j. Yeah, no, yeah?
Yeah.
That's the gradient. That's the direction for the steepest slope of that surface through that particular point. That's what we're talking about. So that's step one. Step two is, hey, you know what? Find the other thing. If the derivative is gradient dot unit, we just found the gradient vector. Got it. Now find the unit vector. A unit vector is always a vector divided by the magnitude of that vector. Can you tell me a vector? If I give you a line between 2 points, can you give me a vector between those 2 points? Yes or no? I need to know.
Yes.
Okay, so that's one thing. Sometimes before when we work with our vectors, it doesn't matter like which one you put first and which one you put second. You have to do that here. The gradient vector has a certain direction. It's telling you I want it in this literal direction. So from this to this, that means when you find your vector, you have to subtract this minus this, and you have to subtract this minus this. If you go the other way, you'll get the vector, the gradient vector you get the unit vector in the other direction. So your slope will change. Does that make sense? It'll be sign-wise changing. We don't want to do that. So for us, we go, okay, well, let's go V from P to Q. That's what I'm going from P to Q, which means that we have -1 minus 2. We get 2 minus 0. That's the vector that you got to have. And not if you're okay with that one. That's what we want. Now, if we want to find out the unit vector from that, well, that's not bad. It's the V vector from P to Q divided by the magnitude. Let's do it right here. Magnitude says square them, add them, square root them. Oh, is that what you get when you add 9 and 4? I didn't even know that. Been a long day. Been a long day. Yeah, no, yes. What do you think?
Maybe.
Okay. Did you get it?
Yes. Yeah.
Do we have a gradient?
Yes.
Do we have a unit?
Yes.
Can you find a derivative? How?
No.
That's it. That's step 3. I know I'm kind of messing up your notation here, and if you want i's and j's or all vectors, I don't care. I'm going to be mixing up just to throw it at you to make sure you understand these are both vectors and they still work. With me? No? You want to change it? Okay, fine. I'll change it. Goodness, okay. Happier? Does it matter? Yes, it matters. I gotta have i's and j's or it's not vectors. Okay. Either way, it's fine. One of the key things I want you to notice is this. When you are doing a dot product and you have just found a unit vector and have that right there, do you need to distribute that?
No.
What would happen is, well, let's see. You distribute, right, to both. You'd be multiplying times here and adding, which means you could factor it all out. So if you look back at the property dot product, you can pull that scalar forward. That's fine. Just dot product your vectors, keep your scalar. That's why we write unit vectors like that, so that we don't have to mess with that 1 over square root 13. So we go, okay, well, this is going to be that 1 over square root 13. Let's dot product the vectors. This is negative 3. This is minus 4. Do you see it? I's being multiplied, that's 1 times negative 3. J's being multiplied, that's negative 2 times 2. Add them together. And then put it back. I guarantee if you distribute that and you distribute your scalar and do your dot product, you're going to get exactly the same thing, but you're going to notice you're going to have a lot of root 13s flying around for a while. Does that make sense? What would you rather do? I'd rather keep my scalar out in front and not have to worry about that. You clear? Now, you might not see that. You might see this. What do we do in that case? What's it called? I might rationalize it, but it's the same exact answer. Now, what does it mean? What is that?
It's the slope of the surface.
The slope of the tangent line to the
Surface.
at
Point.
whatever the point that is. Bless you. Are you done? You sure? You got one more in there? Go for the what is that called? The trifecta or something like that? You should do it. Anyway, at the point on the x-axis, which gives you the point on the surface. Notice that point right there is on the xy plane. X-axis, xy plane. It's giving you the projected spot up to the surface. So it is the slope of the tangent line to the surface at that point, but only in the direction that's going along that line, man. It's parallel to that. That's the point of this. Show of hands if you're okay with it. It's interesting. Listen, this it bears some practice on your own. I'm going to give you an opportunity right now to do that. I want to see if you can actually do that. Can you please practice that one? I'm going to give you some time, like probably 5 minutes. I got to give you a function first. Epic fail. Sorry. Go for it. Do it. I don't know how.
I mean, either. Sorry. Where'd he go?
Okay, there you go. So I want exactly the same thing we're doing here. I want to find a derivative. Same thing. Do the 3 steps. I want gradient first, plug in value. Give me a gradient vector. Yes, it's in 3 variables. Who cares? Same stuff. Find me the gradient, plug in the point. Did you guys get it? That's step 1. Find that. Find the unit vector between 2 points. Find that. Then do a dot product. I'll give you a piece of advice when you're doing the partial derivatives here. There's a certain pattern to it. Once you find the first one, the other 2 are going to be very obvious, okay? About every 10 seconds or so, I'm going to give you a step. So I want to keep you on track. By the way, just to pause you for a second, you can actually rationalize this if you want to. It gets a little better, but if you're plugging in numbers, is it super imperative that you do that? Not really super imperative. You can, it doesn't really matter. It's up to you. If you do want to rationalize it, you end up getting this. You end up getting that because you rationalize, these all go away, you get square root of the same, that's what you get. So either way, you're plugging in one less number here, but whatever. Ladies and gentlemen, did you make it at least that far in this amount of time? Good. Great. Can you please tell me what numbers you should plug in? Is it the 6, -2, 6, or the 4, 2, 2? Does it make a difference?
Yes.
Yes. I'm just going to ask you for the answers. So we're going to plug in x is 4, y is 2, z is 2. Can you tell me what this first component is? Right side people, have you done that?
1/2.
How much?
1/2 5.
1/2? 1/2? So this whole thing, 1/2 I. Love it. How about the next one? Okay. 1/4?
Just one.
1, 1, 1. Let's see. 8. I don't want to do that. It'll be 8 over 8. Yeah, you end up getting 8 over, that whole thing is 16. Square root of 16 is 4. 4 times 2 is 8. 8 over 8, 1. Come on. But then the same thing's going to happen here. You get 1K, yeah? Oh, good. Hey, this is why we plug in numbers now, because that is a whole lot nicer to deal with in a dot product than that thing is. Make sense? So we find our gradient, plug in a number, no problem. You got now a specific gradient vector. That's what we want to have. So events have made it that far. Okay, take some other time. If you haven't done it already, do step number 2. I want a unit vector. Have you done it already?
Yes.
Do you guys need more time, some of you?
Yeah.
Okay, let's take just a little bit. Are you on track? Have you found your unit vector? Are you feeling more confident about this finding derivatives, directional derivatives sort of thing?
Yeah.
Is the gradient just fine now? And you understand what it means, which is kind of cool. So we have this gradient, we have this unit vector. If you have a gradient and a unit vector, dot product, you find the derivative. So if you've done that, great. If not, do it right now. So perform step number 3. Find the gradient, check. Plug in a number, specific gradient. Find the unit vector, 2 points, no problem. We can find a vector, take a unit vector of that. You must have a unit vector. A lot of people make a mistake and just take this. You can't do that. That's not a unit vector. We need that as a unit vector. Oh man. This one dotted with that one. So a multiplier, 1/2, 1/3, 1 times negative 2/3, 1 times 2/3. Those should be gone. So 1 times negative 2/3 plus 1 times 2/3, eliminate, you should get 1/6. Did you get 1/6? For the last time, what is that 1/6?
So it's the line that's like
The slope of the tangent line to the at point in the direction of the line that goes through those 2 points. That's crazy. That's what we're doing. So fans, if you don't actually understand it, weird, right? We're going to do one kind of application problem, be kind of fun, when we come back, and then we'll be done with this section. All right, so our last example. Let's put this to practice. Let's see how a gradient can actually be used in a clearly realistic example here. So there's a certain part of a hillside that can be modeled by this function. Now, before we go any further, let's talk about what that function is. I taught you how to think about surfaces of multivariable functions. You set equal to a dependent variable, we solve it, you get this thing. Anyone in class right now, do you know what that thing is?
That is a graph along the y-axis or z-axis.
Does anyone know specifically what this thing is? Yep. How many squares? Minus hyperbolic paraboloid along the x. So part of this curve, yeah, you could maybe think about that, how a hillside could be modeled by a saddle shape for a little while. So a certain section, not the whole thing, okay, but a certain section modeled by a hyperbolic paraboloid. No problem. You are at 0.32. That means that really if you plug that in, you're at 0.323 root 2. You're on the side of the hill. Does that make sense? At the bottom of the hill, origin, canyon, there are a pack of... I'll make it myself. Killer horses. Yeah. You gotta watch out for killer horses. Killer bees, whatever, but killer horses. Since you didn't pick, you could have picked bears. Could have picked lions, ligers. No, killer horses. So the killer horses that are about to chase you. Now that's bad because they're fast. So we don't want to mess around, okay? We want to find the direction of the fastest path up the hill for that segment. And the heading, if y is north. So you guys know about compasses, right? Compasses choose north as the main, well, main direction, and then we take angles off of that. So if y is north, we're going to figure out a heading on our compass so we can choose the right path. Now, what gives us the vector for the direction of the steepest path up or down a hill? What gives it to you? We didn't spend 3 hours doing this for you to be silent. What gives you the direction for the fastest path up a hill?
Gradient.
The gradient. Let's find the gradient. Go for it. I'm going to do up here as you're doing it, but I want you to try it. Find the gradient. Get the 1/2 power, bring it down. Chain rule gives you a 2. 2 and 1/2 are gone. You get 1 over the square root of that. Partial with respect to y. The 1/2, you bring that down, you got chain rule gives you a 6y, or just think about the 2 being gone with that 1/2, you get 3y. Head nod if you're okay on the partials. We should be, not too bad. From there, we got to make up our gradient. We got no problem. Gradient gives us this I plus this j We're looking good. Now, interpret it. Don't just give me gradient without understanding the idea behind it. What does this give you? What is that? Number one, is it a vector?
Yes.
Is it a vector in 2D or 3D?
2D.
This hill is 3D. You get that, right? This vector is really this vector function that's on 2D. It's going to give us some direction that when we put it in the correct direction, we're going to climb the hill over that vector. That's the idea of what a gradient does. So this right here is the vector function that gives you the path of steepest ascent at what point? Here, at any point right now. What point do I want to find it at?
2 or 10.
At that point. So let's find the gradient at that point. Hey, I'm there, right? Well, I'm actually here, but it's based on x and y. I'm there. I want to find the steepest path away at that point. So right now I'm going to stop before the horses start running. I'm going to do all my math, right? I'm going to figure out, horses, you wait. Whoa. And I'm going to figure out this vector first so I can run in the correct direction. I'm obviously not going to just start running. That's just ludicrous. So figure this out. And 18. 18? Okay, barring simplification, and I'm not going to for a certain reason, I'll show you why in a second. That right there is what? Come on, what is that?
Gradient.
I know it's the gradient. You're right, it's the gradient. It's the gradient at that point, but what's it mean? Come on, what's it mean? What's this?
The direction of the
It's a direction in 2D that's telling us that says you need to run. So if this is 2D and we have the surface, you need to run over that vector basically away from that point, away from the origin, run along that vector to climb the hill as fast as possible, as steeply as possible, we'll say. That's the direction of quickest ascent of that hill modeled by the hyperbolic paraboloid but only at that point. Now that kind of says something. As soon as you take a step, does that path change?
Yeah.
Yes.
And so of course you're gonna have to stop and redo your math and take a different path. But for the first step, you're gonna know that's the path, that's the direction, that's the path. Now, how about this? Can we make it a little bit nicer? I'm gonna do a couple things here. Firstly, could you tell me the rate at which you will be climbing the hill if you go along the fastest path of ascent? Can you tell me the rate? What is the rate of change in calculus? What is it? It's a derivative. Could you find the maximum value of the derivative from this right here?
Yes.
The maximum rate of increase we found this out, we did a proof on it. The maximum value that the derivative can attain is the magnitude of your gradient. Because if that gives you the path of steepest ascent, we proved that the unit vector would have to be exactly the same direction. That means cosine would be 0. You get 1 times 1, that's unit vector times cosine of 0, that's 1. You basically get the magnitude of that gradient. So if I want to figure out the maximum rate of change, maximum rate of ascent, that's going to be this. That's going to be that. Head nod if you're okay with that. Okay. So if we do that, if we find the magnitude of this, man, the first thing I'm doing, if I'm finding magnitude of that nasty vector, what are you doing first before you do anything else on that one? Yeah, please factor that scalar. Factor the 1 over square root 18 out. You can simplify that. You can get 3 root 2. I don't really care at this point, but at least factor that out. So, factoring that scalar 1 over square root 18, we get square them, square your components, add them, and square root them. If you just can't stand the work that I didn't simplify it, and you really want to simplify it, this all simplifies down to square root 74 over 2. That's over 6, sorry. Question?
Should that be the square root of 37?
Yeah, it should all be inside the rest. Yeah, I was gonna.
Oh, yep. Yes, it should be the square root of 37. This is magic happening. You're being chased by killer horses. Magic can happen when you're being chased by killer horses, okay? So square roots just disappear. Probably crap your pants a little bit. Anyway, yeah, square root of 37 over square root of 18. If you want to simplify that, you get square root of 74 over 6. Thanks for that little point. What is this? What is that number right there? What is that?
The rate of change into your first
So rate of change, you're correct. What is the rate of change?
slope.
That's the slope. That's the derivative. If we said the maximum value of the derivative happens at the magnitude of your gradient, then that is the maximum slope that's away from that point up the hill. That's the maximum slope we can have. Head nod if you understand what I'm talking about there. For real, you understand that. You understand that this actually gives you slope. The magnitude of a gradient is a slope. In fact, it's the maximum slope that you can have at that point of that surface. With me? Cool. Now let's that's the direction you're taking, right? But that's kind of hard, right? Because we don't have just this XY system under us that we can run up a vector. So let's talk about something a little bit different. Let's talk about the heading. So starting with our direction vector, our gradient of steepest ascent. Can we figure out what heading that is? look, if you're trying to figure out what heading that is, heading has the connotation of degrees. It says what degree? I mean, should we be at 30 degrees, 60 degrees? Heading's going to give you some degrees off of true north. That's what's going to happen. So, wait a second. The gradient is a vector, right? That means it should have an x component and a y component. By the way, gradient's on the plane, right? Even if you're in the mountains and you're climbing a hill, do you understand that if you flatten out the earth and use true north, doesn't matter if you're climbing or falling, north is still north. You with me? Your heading, still your heading. It's based on the plane, even if you're climbing. So what's my x component? What's my y component? Okay, so if I want to figure out my angle here, well, then I can take tangent and put y over x. In other words, I can take tan theta and put 6 over square root 18 over 1 over square root 18. My y over my x. That's how tan theta works. It's y over x. What's going to happen here? Gone. We get tan theta equals. Now, I don't have a super cool unit circle that puts 6 on it, so we're going to kind of approximate here a little bit. So can you give me the angle based on degrees? If tan theta equals 6, can you do a tan inverse on 6 and make sure your calculator's in degrees? And tell me what that is. Can you say that louder? I didn't hear you.
80.53 degrees.
80.5 something?
Yeah.
Let's call it 80.5 degrees. Head nod if you're okay on that one. Left-siders, yeah, no? If you're still awake out there. Can I show you something? Just so you understand what you can and what you can't do. Please watch. For finding the steepest slope itself, you may not change this freaking vector. You may not change that. For finding heading, heading has nothing to do with the slope. Heading has to do with direction. It's two-dimensional. It doesn't even matter as far as the slope is concerned. You can do things like this. Instead of taking this whole vector for heading, you could have made another vector, which eliminates that scalar multiple. It puts it in a parallel relationship with this. You could have just considered I plus 6j by removing out that scalar multiple. It's still parallel. It's still the same direction. It just has more magnitude. Does it matter for heading? No. It's like saying I'm going this way or I'm going this way. It's the same way. Okay, it doesn't matter. It would matter for the slope. So you can't change it for that to find the actual max rate of change. But you can change it for this. If you notice this is still 6 over 1. You're still getting 6. Do you guys see that? So for heading, yeah, you can do things like that and make it easier. It doesn't really matter, but you can do it. Also, how about this one? Before we do anything else, what would the maximum rate of, this is the maximum rate of ascent going up the hill. What's the maximum rate of descent? Negative of that. The vector would be negative of this, just minus minus. That would be called suicide, because you're going to go. So anyway, now, one last thing about the heading. One last thing. I made a statement here. If y is north, when you are doing this, you are always treating this as 80.5 degrees from the x-axis. From the x-axis. So, how many degrees from the x-axis to the y-axis? There's 90 degrees. If this is 80.5 degrees from the x, how many is it from y, from north?
9.5.
So from north, that should be your heading. So here's what's going to happen. I mean, this is obviously what you're going to do. So you're going to stand at the point. You go, oh, hey, this is modeled by a hyperbolic paraboloid. That's this particular function. Let's find the gradient. Work it out real quick, no problem. Say I'm approximately at this point from the origin, so you can plug that in there. You can find your vector for the steepest ascent. And then what you're going to do is figure out what your angle is from x, subtract from 90, and go, I gotta have, here's north, I gotta have 9.5 degrees east of north from that. And that would be, it's actually relevant, I'm joking, but that's the direction that would give you that's the heading, that would give you the steepest path up that hill. Does that make sense? Heading doesn't care about your altitude. It doesn't care whether you're climbing or falling. It doesn't care. It's just pointing you up the hill in that direction. So long story made real short, the direction of maximum increase is called the gradient. The direction of maximum decrease is called the negative of the gradient. The actual rate of maximum decrease or increase is the magnitude of the gradient, because that's the important vector we talked about for all of the day. Oh, and by the way, you can't outrun horses. All right? They're fast.